Can black holes evaporate? Imagine the most extreme object in the universe. A black hole. Its gravity is so powerful that once something crosses the event horizon, nothing, not even light, can escape. For decades, this led physicists to believe that black holes were truly black. They could absorb matter and radiation, grow larger, and remain in the universe almost forever. But in 1974, physicist Stephen Hawking discovered something extraordinary. According to quantum physics, black holes may not be completely black. They can slowly emit radiation. And if they continue losing energy for long enough, they may eventually disappear. This phenomenon is known as Hawking radiation. But how can anything escape from an object whose gravity traps even light? To understand that, we need to look at the strange world of quantum physics. Empty space isn't really empty. According to quantum field theory, even what we call a vacuum contains quantum fields. These fields are never perfectly still. They undergo tiny fluctuations, even in apparently empty space. Now place an event horizon inside this quantum environment. The extreme curvature of space-time around a black hole changes how quantum fields behave and, crucially, how different observers define particles. The result is remarkable. To a distant observer, the black hole can appear to emit a faint thermal glow. That glow is what we call Hawking radiation. You may have heard another explanation. It says that pairs of particles appear near the event horizon. One falls into the black hole, while the other escapes into space. This picture can be useful for visualization, but it should not be taken as the exact physical mechanism. The real explanation comes from quantum fields evolving in curved spacetime, and the mathematics predicts something astonishing. A black hole has a temperature, but this temperature behaves in a very unusual way. For black holes, the smaller the mass, the higher the Hawking temperature. A massive black hole is incredibly cold. A stellar mass black hole, several times more massive than our sun, would have a Hawking temperature far below the temperature of the cosmic microwave background that currently fills the universe. So today, astrophysical black holes generally absorb more energy from their surroundings than they lose through Hawking radiation. For them, evaporation is unimaginably slow. A black hole with roughly the mass of our sun would require around 10 to the power of 67 years to evaporate through Hawking radiation. That is vastly longer than the current age of the universe, which is about 13.8 billion years. And supermassive black holes can survive for dramatically longer still. So we will not be watching the black hole at the center of our galaxy evaporate anytime soon. But imagine the universe in an almost incomprehensibly distant future. Stars have burned out. Galaxies have faded. The universe has expanded and cooled enormously. Under suitable conditions, black holes would eventually lose more energy than they gain. Then evaporation could dominate. As a black hole emits Hawking radiation, it loses energy. And because energy and mass are related through Einstein's famous equation, E equals mc squared, losing energy means losing mass. As the black hole becomes smaller, something strange happens. Its temperature rises. A hotter black hole radiates more strongly. It loses mass faster. That makes it even smaller, which makes it even hotter. So evaporation accelerates as the black hole shrinks. Near the final stages, our semi-classical description predicts increasingly energetic radiation. But what exactly happens at the very end? Does the black hole disappear completely? Does it leave behind some tiny remnant? Is there some new quantum gravity phenomenon? We don't know. At sufficiently small scales, the physics requires a theory combining quantum mechanics and gravity, a theory we do not yet possess in complete form. And this uncertainty leads directly to one of the deepest problems in modern physics. The black hole information paradox. Imagine throwing a book into a black hole. The book contains information, the arrangement of its atoms, its structure, everything required in principle to describe its physical state. According to quantum mechanics, information should not simply be destroyed. But if the black hole eventually evaporates into apparently thermal Hawking radiation, what happens to the information about everything that fell inside? Is it somehow encoded in the radiation? Does it remain in a final remnant? Or does our understanding of space-time itself need to change? Stephen Hawking originally argued that information could effectively be lost. Later, he changed his position and accepted that information should ultimately be preserved. Today, many physicists believe information is not fundamentally destroyed. But precisely how information escapes or is encoded during black hole evaporation remains an active area of theoretical research. And that makes Hawking radiation incredibly important. It forces two of our most successful descriptions of nature to confront each other. Einstein's general relativity, which describes gravity and spacetime, and quantum mechanics, which describes the microscopic universe. Black holes sit directly at the intersection. There is one more remarkable fact. Despite its enormous importance, Hawking radiation from an astrophysical black hole has not been directly detected. For known black holes, the predicted signal is simply far too weak and cold compared with radiation in their environment. So Hawking's prediction remains a profound theoretical result rather than a directly observed glow from a real astronomical black hole. Yet it completely transformed our understanding of these objects. Black holes are not necessarily eternal. Given enough time, and under the right cosmic conditions, they can lose energy. They can lose mass. And according to our current semi-classical understanding, they can eventually evaporate. So perhaps the darkest objects in the universe have an ending after all. And hidden inside that ending may be the answer to an even greater mystery. How gravity, quantum physics, space, time, and information ultimately fit together.